fixing problem. Sushmita, take it away.
Thank you, Rohit. Good morning, everybody. It's wonderful to see such a large gathering. It's almost as maybe even better attending than some of the festivities sessions. So I have been to IIT Gandhinagar twice before, but that was quite a few years ago, and I just coming back this time, it was like absolutely eye-opening. It's one of the most beautiful, well-maintained, well-kept campuses I have been to. So thank you so much for having me. Okay, so without further ado, let's talk about what is it that the title says, how to influence competition. Let's consider knockout tournaments, whatever that means. Any sports competition where you have the format is winner go forward, losers go home. Okay, that's a general standard of a knockout tournaments. Now, of course, there is a FIFA World Cup sort of a photograph. It does not necessarily have the knockout format all throughout. There's a round robin, and then the knockout part sort of starts. Now, this is the middle picture is that of a recently concluded World Chess Championship. Now you may ask, is that really a knockout tournament? Well, yes, one person, there were only two players, they were playing against each other. The person winner took the prize, the loser went home, that sort of thing. Okay, tennis competitions, probably the most prototype of a single elimination tournament, right? The standard ATP, WTA competitions at least. So more generally, the thing that describes this knockout tournament can also be ascribed to other sort of decision-making processes where you are sort of considering a plethora of choices, and somehow people are trying to come to an agreement onto a final outcome, and you, in a sort of a round fashion, you eliminate some choices, and then next step again, some type of collective decision making process takes place, and then again some more decision possibilities are discarded, and sort of the process sort of continues there onwards. Okay, so that's sort of the world that we are talking about. So in this realm, there have been a lot of work of very many different kinds. Sometimes it's about what kind of decision-making sort of process one should use to come to a decision so that it is fair and it's balanced and so on and so forth. That's generally the realm of social choice theory and particularly voting literature. But there are also other things. There are manipulation, like if you want to enforce an outcome, what is it that should happen? Especially if the decision-making process is decided a priori, is there a way that some people, like maybe the players, the individuals that are participating, or an outside entity, an organizer, or a central body can somehow affect the outcome? So stated in terms of sports competition, that comes to asking, if we had a favorite player, is there a way to ensure that this favorite player wins the tournament? Right? Okay, so I should say that I have given this sort of talk, like I've been working on this topic for a long time, and in previous years when I used to give this talk, I used to completely motivate this and really from the perspective of sports competition, because that's what I like talking about, and so I think it makes sense for a lot of people, but I think you should be more creative in trying to see where all these things sort of apply, okay? So I'll be using sports terminology, brackets, seedings, and so on, so people who are familiar, who watch sports, follow sports, and so on, would have an intuitive understanding of what this is. And of course, we make it formal as we go along. But the terminologies are borrowed sort of with this in mind, that they actually capture this knockout tournament type scenario, knockout sporting competitions. Okay, so what do we have to work with? Firstly, we have the possible entities. In this case, let's call them players. We have some type of predictive information of if this player plays this other player, who is likely to win. Okay, so without that, it's not at all clear how one can affect the tournament, right? Now the question is, if the player does not If you're sort of supporting a player who can beat everybody, then you are in sort of good company. Then there's not much to do. Pretty much any bracket or any seeding will ensure that this person wins. But it might be the case that this is not an all-powerful player, and there are opponents to whom this person might lose. Then the question is that like game over, so to speak? Like there's nothing that you can do to affect the outcome. Right? It turns out, as anybody who has watched any sports competition would see, that sometimes, if you're very lucky, the way the initial seedings or groups happen, it can be that your favorite player does not actually have to face an opponent it cannot beat. And they have a path towards a higher outcome further down in the competition than they otherwise would. It happens all the time. There is a lucky draw that happens earlier in the competition, most competition, not everywhere. And sometimes luck plays a role there, right? So that's one way for us to possibly affect an outcome, that we find a path for our player to proceed through the competition so that this person emerges the winner, basically by not having to play anybody he or she cannot beat. Okay, so the type of competition that we are talking about here, I'd like to give you an example, is this, okay? So you have, let's say, 8 players. So in the way to read this is, it's a seeding. So the way to interpret this is, in the first round, this player, I don't know if you can read it. Okay, V1 plays V2. That's one of the first round match. Somebody wins, in this case, V1. Another first round match involves V3 and V4. Somebody wins, V4 wins. Then V5 and V6. Again, there is an outcome who wins? I am having difficulty reading V5. Okay. And then V7 and V8 play and V8 wins. Okay. So this constitutes the first round. In this case, I'm implicitly assuming that the first round consists of basically even number of players. Otherwise, this sort of pairing cannot happen. Now, in more general terms, there are competitions in which not every player has to play every round. They get buys in earlier rounds and they can join the competition later on. But for the purpose of this talk, we'll be talking about a balanced competition where everybody has to play every round, okay? Like a traditional tennis championship. Okay, so round 2 involves players who have won round 1. So in this case, please take note of how the seeding happens in the second round. The fact that V1 and V4 were sitting sort of not consecutively, but adjacent to each other in the 2 pairs is what tells me that they will be playing each other in second round. Okay, and the same logic applies to the other 2, which is that V5 will play V8 in the other second round match. Okay, somebody emerges the winner, V4, I take it, and then in the other outcome, so V8 emerges the winner. So this is the final round because there are only 2 players left, and whoever plays, whoever wins, is declared the winner. Okay, so this is the sort of, okay. So what are we then asking? The only sort of the control we have in this scenario is that we can tamper with or manipulate that seeding, because that seeding is what is deciding any player's path to the final round and whether or not he or she can win, right? Okay, so that is the question. So formally stated, what we have is a win-loss, or sometimes it's called strength diagraph, a tournament diagraph. I am using the word tournament so many times, so therefore I sort of thought of using this win-loss graph. But a tournament diagraph is basically a complete graph on any number of vertices where every edge has some direction. That's a tournament diagraph, okay? And we'll call it a win-loss graph. And the question is, does there exist? So the arc direction here tell me that and star is the player who's my favorite. This is the person I want to see win. So the arc directions are such that if C and E were to play each other, C would win that outcome, that matchup, okay? If star, the favorite player was to play B, then who's winning? Okay, favorite player is winning. Okay, but look, if star were to play A, he would lose. Okay, so to make star win, I must ensure that star never has to play A. And how do I do that? Sorry? Ensuring that this A player plays an opponent who can beat him, and then create these sorts of situations so that the only person who emerges from that side of the bracket, from that part of this competition, is actually somebody star can beat. Right? That's one way. Okay. So this question was introduced. So this kind of questions have been studied in sports analytics forever and ever. I mean, there's a huge literature on that. Empirical studies have been done and so on. But formally, in the way that I am stating it, it was posed by Shoham in Amas 2009. And since then, there has been a steady and sort of ever-growing body of work centered around this question. Okay, so I ask you, how hard is tournament? How hard is it to answer this question? Whether I can ensure a given favorite player can win. So again, there are some trivial, easy cases. If your favorite player is somebody who beats everybody, that's a trivial thing, right? Any seeding works. It does not matter. And this is easy to decide. You just have to check this adjacency, a matrix, or whatever adjacency relationship. If the win is good, so your favorite player is not the most powerful guy. It does not beat everybody. But the win of the graph is acyclic. Then can we say, then is it easy to decide? Then also it's easy to decide. Because, okay, I'll leave it to you. It's very simple. It's a very easy argument, basically reduces to the first case. Like, because there are no cycles, just in terms of what these cycles actually do. Else you will hear the answer sort of in like maybe one or two slides. In general, okay, it's NP hard. So in general means when we have no information, when the Windler graph is an arbitrary tournament digraph, then it is NP hard. And the hardness was shown by Aziz et al. In 2014, like about 5 years after the problem was actually posed. And the reduction is from SAT, okay, 3 SAT. So the takeaway from here is, I work primarily on parameterized algorithms and so on and so forth. So seeing a problem being NP hard does not phase me out. Basically, the work starts right there. Like that's the starting point. So the question is, why is it NP hard? It was not hard when it was an acyclic graph, but it becomes hard when it's an arbitrary graph. So basically, cycles play a role. Right? It's a cycles that make the problem complicated. That's how you can sort of decide. That cycles also make it possible. So when cycles are also what makes it possible. If you have a directed acyclic graph, unless the favorite player is the player who sits first in the topological ordering, there is no chance that your player might win the whole thing, right? But cycles, presence of cycles is what allows some player who's not sitting at the very first position of the topological ordering, may have a path towards the final outcome. Okay, so basically, what I'm talking about is this sort of scenario, the players I can't beat have to be beaten by players whom I can beat. So these are strictly weaker players than me, but somehow they're beating a player who's stronger than me. This is the very essence of an upset, right, in a sporting terminology. Formally, this sort of thing would be called a feedback arc set. These sorts of things, when a weaker player beats a stronger player, right, that's what is sort of generally captured under feedback arc set. And the vertices, the smallest subset of arcs whose removal makes the graph acyclic is the feedback arc set number of the graph. And correspondingly, the vertex number version is fewest number of vertices whose removal makes the graph acyclic is the feedback vertex number. So let's see what actually the feedback arc set tells us. Okay, so we have this graph, we have a ranking. This ranking is obtained by, suppose you remove the feedback arc set of the graph. Remove those edges. Now you have a DAG, right? Because by definition, feedback or removal of a feedback arc set gives you a DAG. You can now do topological ordering. That's what this is. See A, B, C, then the star, E, F, G, H. So my favorite player actually sits bang in the middle. It's not one of the strongest, it's definitely not the strongest player, right? It's somewhere in the middle. And you, these red arcs that are going back are these upset arcs. Okay. And all the black arcs are going forward. They show that A is stronger than B, and A beats B, A beats C, A beats star, and so on and so forth. The only person who sits to the right of A that A cannot beat is this guy, F. Okay. So this is the work. Just taking this perspective in mind, this feedback, huge amount of work has happened studying this problem from the perspective of parameterized complexity, exact exponential algorithms, and so on. And people have also explored a lot of structural properties. So next, I'm going to give you a very incomplete landscape of the type of problems that have been studied. So I had the very ambitious goal of having one slide in which everything will be there, like every known result that I know. I asked some of my colleagues, are there any extra stuff in there? I was like, I can't even make this slide. It's just too complicated, and it'll be just too too cumbersome to stare at. So I'm going to give you a chosen sort of a snapshot of this world, and there are lots of other things. Please feel free to come and ask me. Okay, so let's take the tournament fixing as the first problem. One of the set of results are that of structural properties. They literally talk about when does a favorite player always have a winning seeding. It might be, for the acyclic case, we talked about it. There can be some more structural properties, sufficiency conditions, even when you have cycles. Okay, so those are what comes in. There's this notion of a king. King is a player who either beats another vertex or beats somebody else who beats that vertex. So it is basically has distance 2 from every vertex. That's a king. A super king is a more generalization. It's a super king is somebody who either beats another player, beats more than other players who beats that guy that he cannot beat. Okay, so these, if your favorite player is a king or a super king, then you always have a winning seeding. And there are lots of other things based on degree, out degree, in degree, blah, 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 and so on. Then comes the next set of results. Parameterized algorithm, specifically looking at these two objects, feedback arc set, which I ask you to keep in mind as upsets. And notice one thing, it's a theory crowd, so I don't necessarily need to sort of motivate what it means in terms of a parameterizer, like how small or big. But you understand that in a general sporting competition, there aren't too many upsets compared to the number of games that are played. So if you think about parameters as objects that need to be of small value compared to the size of the entire competition, number of upsets seems to be a meaningful parameter. Okay. Feedback vertex set would be the number of players, fewest number of players who participate in these upsets. Okay, so maybe there's one team or player who participates in lots of upsets. Okay, so that's the sort of thing. So the first result in this direction was ILP based. It explored some structural properties, and we'll talk about that in the second part of the talk. And then had an ILP formulation which checked for feasibility. The next, the first one was Ramanujam and Steven Zeider in 2017, followed by we improved that algorithm by removing the ILP part, doing a little bit more of structure, the exploration of the structure, and then doing a greedy type sort of hacking step where you sort of really build up the witness. There's a kernel. Kernels are more sophisticated, more refined sort of algorithmic condition than just an FPT algorithm. Kernels say more than that. Kernels can be seen as sort of efficient pre-processing. You can basically compress the instance of a problem into a very small size, a function of the parameter, in this case, feedback arc set. And there was another paper which showed, which was several years later, it's conceptually even more sort of evolved, involving feedback vertex set. In this In the same framework of tournament fixing, we also studied this question of bribery. That if your player, the favorite player, does not have a seeding which allows it to win, what is the fewest number of arcs you can flip so that your player wins the tournament? Now notice, if I'm assuming that the number of players here are powers of 2, because everybody has to play every round, there are at most log n rounds. So obviously, if I could bribe every opponent who will play against me, that is, I have log n number of reversals, I can win any competition. So really the question is, can you do in strictly less than log n time? The log n number of arc reversals. And there was an exact exponential algorithm and also feedback parameterized algorithms studying this setting. Now, in the world of tournament fixing, I imagine somebody would raise this thing. Why is the strength graph, this win-loss graph, deterministic? Nobody actually knows. That's why we even have competition, that who will actually win against whom on the actual day of the competition. So this information of this player is stronger than that. It's like, or this player team will be, this other team is at best probabilistic. Right? So that's the most natural setting in which to study these things. And that was the setting in which it was posed originally. But I think the probabilistic, somehow that probabilistic version of the problem got cast aside for a while because it was conceptually harder to handle. People worked on the deterministic thing. And now we have come back and now we are addressing the probabilistic setting. Okay, more on that a few slides later. There's also a version of this problem called, not the way I stated, it's called challenge the champ. So it's like two people play, whoever wins is declared the champ. Other players come in, join this thing, and they play against each other, the champ, and then whoever wins that outcome is declared the champ. So basically, at any time, players are playing against the current champion. Okay, and then finally, you exhaust all the players and the champion is declared. Lot of game competitions actually follow this format. So the reason to put this here is because it also uses, so the color, here also people have studied the probabilistic setting. This was studied slightly before the probabilistic analysis on tournament fixing. Okay, so this is why I'm saying that people are now looking at the probabilistic model and addressing these questions. So naturally, we can say that having a particular player win the tournament seems like an absurd objective on the part of the tournament designer. I mean, they really don't care actually who wins. What they want is to maximize their profit, like, spectators, viewership, social media engagement, etc., etc. That's what they want. So we can agree that some games are more attractive for whatever reason, historical rivalry, some notoriety of some players, animosity with teams specifically for no reason whatsoever. That seems to happen, be quite common in this sporting arena and so on. So some games are more attractive than the other. And naturally, from the point of view of the tournament organizer, you would want to sort of ensure that those games happen, right? I mean, most of you are probably cricket fans. You know that if India and Pakistan played cricket World Cup, it will break all records. Final of cricket World Cup, it will break all records. I mean, it will probably break records if we played final of any other competition, but we don't seem to be doing very well in others. So this is the only best hope we have. And I tell you, and despite best efforts from all the parties, ICC, BCCI, and all other stakeholders, this pipe dream has not actualized yet. Okay, so the point is, if we are trying to talk about control, like designing a tournament to affect a certain outcome, a possible outcome could be somehow maximizing popularity. So here, there can be multiple sort of ways of doing it. One is score-based, the kind that I said. Some games are more valuable than the other for whatever reason. Do you want to sort of somehow create a seeding where the chances of those games, higher value games happening are likely? Right? Okay. So this too has been studied by Chaudhary. So I should tell some of the initials. I'll tell you the ones which are not mine, like G means me. But other than that, this Chaudhary, Henry, Moulton, and Zahavi. And this is this year's paper. The other one would be also the kind that I said. If the tournament organizer said, well, we don't really we are not trying to maximizing some score, but we want to precisely guarantee certain matchups. Like India and Pakistan have to play at some stage of the World Cup. Okay, one obviously of doing it is to do round robin. Everybody plays everybody, so they will also play each other. Okay, but that's not really a knockout tournament. Okay, so these are the two types of things where who wins the final tournament is of no importance. It's just that it's cool. You're just trying to maximize some objective. Now in this, okay, so the thing that I said was on the unseeded setting. A more realistic scenario in which tournament design actually happens is the type that happens in tennis, which is that 32 players play, they are seeded, and the way they guarantee maximum viewership is to say that we'll create a bracket so that the first two seed can only play each other in the final, right? Seed 2 and seed 4 can only play each other in the semi-final, and so on and so forth. So that's what we are calling the seeded setting. So there's this paper last year, actually this is the journal version, the conference paper appeared a few years prior to that, where they explored the same structural properties that were looked at before in terms of tournament fixing, right? But now in the seeded settings. And they show that many of the conditions that are sufficient here no longer apply here. And if you have this sort of additional constraint of respecting seeds, and they also give other structural properties which will ensure like that those are sufficient conditions, how to ensure that this tournament fixing actually works. And here the outcome is again so that one particular favorite player wins. So that's why the sort of it's hanging from that part of the tree. So how much time do I have now? Okay, good. So that sets me up. So that landscape that you saw, there's a common thread running through all of them. Okay, so I'm just going to discuss the steps broadly, and then we'll see an example and see how far we can go with that. So first is to explore the structure that witnesses a solution. So we agreed we have the input graph, which is on n vertices, and it has n squared edges. If I were to try all permutations, right, it would be an n factorial number of tries. That is not FPT. It's not efficient algorithm. So the point is, can there be some type of you explore the structure of the win-loss graph and the problem you are studying and come up with some witness that can be succinctly represented. So what I mean by the succinct representation is that you're able to compress the structure and preserve enough relevant information that when that is missing here can be added in some meaningful way so that it can be expanded to a witness. Okay, so what that succinct representation is really varies from problem to problem. But this is where all the creativity comes in. I mean, I'd say that. Now we need, because I'm talking about parameterized algorithm, I need the succinct structure to be of size, some function of the parameter. Third step is to be able to enumerate all such structures in some function of the parameter amount of time. Okay. And that should be step 3. Step 4 is now you have this structure. There are information stuff missing there. Take all the other players that you have not put in the structure and try to put it and see whether you can expand that succinct structure into a full witness. Okay. So if such a thing can happen, you have actually created a witness, a solution to your problem. And if it cannot happen, then you have no instance to the problem. Okay. Is this broad template clear? Okay. So let's see an example. So let's go back to the original problem. What do you think would be a succinct structure just to witness this fact? What would be a witness to this problem, whether V star can win this if there is seeding that allows V star to win the competition? It's this object called, I'll just move through it. It's a nice sort of, I think, experiment. It's not very difficult, but if you think about it, basically, it's a recursive structure that needs to be defined, that needs to hold, which is that this player has to play somebody in the first round. All other players also need to play somebody in the first round. Hopefully, your player, your favorite, will win the first round match, and he will have to play somebody that he can beat in the second round. So that's the next set of edges, blue or green, I can't tell, sorry. And then finally, now there are only two players missing, so E and a star, right? So this is the final match, which is that of the gray. And in order for the favorite player, star player, to actually win the final outcome, the person who plays in each round is somebody he can beat. Okay? So what this means is, what this object is, it's basically a subgraph within that big win-loss graph. It's a rooted tree. It's kind of an outbranching, which has this weird sort of a size thing. It has the root node has a child of size 1, a leaf. It has a child that supports a tree rooted. It has a child on whom there is a tree of size 2 power 1, another child with tree 2 power 2, and so on and so forth. Okay, so it goes all the way up to 2 log n, 2 to the power log n. So this is the basic recursive description. This is called generally a binomial arborescence when such objects exist. Now, when you want it to span over the whole graph, because we want a complete tournament, it's called a spanning binomial arborescence. Okay. So instead of doing n factorial amount of search looking for all possible seedings, we are basically doing a subgraph isomorphism looking for this pattern graph. A pattern graph where the root is pre-decided, V star. Do you have such a tree rooted at V? Okay, so now tournament fixing in terms of an SBA was basic. So this connection was given by Virginia Williams into this 2010 paper. And the number of results that have explored this sort of connection with binomial arborescence is large. You can see 7. This is the last time counting. Okay, all of this use this connection with binomial arborescence. So for the technical part of the talk, yesterday somebody said a good talk consists of one joke and one proof. There's no joke until now. Let's see what happens in the future. So of the proofs that I thought of discussing, I thought one should probably discuss the one that is most realistic, the one where you don't have perfect information, the probabilistic setting. Okay. So in the probabilistic setting, you have a matrix, n by n matrix, n being number of players. Each entry tells me what's the probability. So entry ij tells me what's the probability that player I, when playing j, beats player I beats j. So the diagonally opposite entry tells you the opposite information. Okay, and the diagonal entries are 0 because players don't really play themselves. You have again a favorite player alpha star, and you have a positive real P. So now one can ask this question in terms of maximizing this also. We talked about the decision version of this question, right? The question is there a seeding such that, so given this information, is there a seeding such that our favorite player wins? There exists a seeding such that the favorite, when you construct the bracket based on that seeding using this probabilistic matrix, the probability that the favorite player wins is at least P. Okay, so it's a high probability event that we are analyzing. So this is an example. You can see it's the tree. It basically says that if player 1 and 2 play each other, there's half and half chance of each one winning. So this is why red, when player 1 wins, it's red, and this is blue. So half and half, so either one. So who wins, that person gets to label this vertex. Whoever wins this match between 3 and 4 gets to label this vertex. Now these are probabilistic events, so the thickness of the edges basically represent the probability that that might happen. Okay, the green player wins or the gray player, blue or red, and so on. So I guess player 4 has the best chance of winning, and it wins with probability 6 by 10. You can just see it's just multiplying. One thing to note here is when player A is playing B, that is independent of player A's winning chances against any other player at any other step. Whether player A gets to a certain round, but what happens, the outcome of a particular game, that's independent of all other games. Okay, that's something to keep in mind. So the main, okay, so the first step in the template is experiment in this probabilistic tournament setting. Okay, where we try to see what would be a witness, and then think about how to succinctly represent it. So here we spent quite a bit of time, and initially we just about one probabilistic error and so on and so forth. And it seemed to be fairly confusing. Then something happened, having spent some amount of time, that there exists a way to completely get rid of all the probability and do a total reduction to this problem, to an auxiliary deterministic problem, solve that problem and transfer the sort of result onto the probabilistic setting. Okay, and that is based on a thought experiment. So we'll go a little bit fast now, but I hopefully you'll catch it. So we view the instance of this probabilistic tournament fixing, even though I told you in terms of a probability matrix, you can look at it as a graph. The values which are 1, they are like edges, they have to exist. The values which are fractional, they are as if they are probabilistic edges. So think of them as the orientation of that edge depends on the probability value. So A tends to B is then the probability A B, the entry, and the opposite is 1 minus 2AB. Okay, that's the way we look at it. So you think about this probabilistic digraph where there are some certain edges that are deterministically value 1. And the others are the probabilistic edges. Think about how we can extend this deterministic part and simulate this random experiment in all possible ways. If there are k different probabilistic edges, there are 2 to the power k number of ways you can orient the edges of these probabilistic edges, right? That's clear. Now consider, so each of these completions are like the completions of that certainty diagram. I'm calling it that just because it's easier to sort of think. Among all these 2 possible ways of completing them, like creating this deterministic object, deterministic digraph, is a subset of these digraphs in which you actually have this favorable event that your favorite alpha star wins with probability P. So each of these diagrams D1, D2, and D to the power 2k, each comes with a probability value based on how the edges were flipped and so on. So you can actually aggregate all those possible events which correspond to probability P star. When using a simple union bound, you basically, one can argue, I'm just skipping a little ahead, to show that what we are basically needing to solve is this problem. You have a set of digraphs on the same set of vertices. You still have the same alpha star. Now you're asking, is there a common seeding such that its favorite player alpha star wins in all the brackets sort of constructed from this seeding for each of these digraphs? Okay, that's what it is. So if you solve this with some, say we can solve this in time t, then using 2 pi k, by 2 pi k, basically 2 pi k are the all possible completions of those digraphs, certainty digraph, and possible subsets of them. That's why you get that overhead of 2 pi k. And then this t is the time taken to solve this problem. It's a Turing reduction, and then you can basically answer the question. So to get a FPT type algorithm, what we have to do is solve this simultaneous tournament fixing using within parameter. This t has to be expressed properly as a function of k. Okay, so now I'll just rush a little forward. I'll say that simultaneous tournament fixing is NP hard. It is NP hard even when one of these 2 values are held constant. So you have a bunch of digraphs. There might be a common subgraph across them. If you look at the feedback offset among that common digraph and use just that as a parameter, you don't get an FPT algorithm because you have NP hardness even when that value is 0. And similarly, for the number of private arcs are basically arcs that don't appear in every other digraph. Okay. So the best we can do is hope for a FPT algorithm, f of k, this kind of an algorithm. See, the explosive sort of exponential growth is just sort of constrained within this. You can only hope for this type of an algorithm when k basically has both this information, the number of upsets in the common tournament and the number of private games. Sorry, what happened? It's like being sort of, I don't know, they play music to just walk people out of the stage, right? That's a bit like that. Okay, now, okay, I have my cue. So the point now is we have an auxiliary structure. We got rid of the probabilistic argument that was difficult conceptually at the beginning and stumped a lot of people for many years. Now the question is, what is the sort of witness? So the witness that worked in those earlier papers, that SBA, does not quite work here. I mean, I can't say it does not quite work. I'll tell you what the conceptual challenges were. Here we are dealing with n different digraphs. So basically what we are saying is, can we have this many different number of SBAs, right? Because the digraphs are different. All of whom exist within their digraph, their subgraphs, and rooted at V star. And on top of that, right? So this was the sort of thing. It was sort of hard to how to maintain this sort of a simultaneous version of this thing. So instead, what we did was we have this sort of character. So this is a complete binary tree of what actually happens in the match. Two people play in the first round, one person moves up. Second, this sort of thing happens second round, third round, fourth round, and so on. So what we're trying to do is create a labeling for the leaf which propagates upwards. Okay, and this object has to respect all the sort of all the n different digraphs. That was basically the bottleneck. Okay, so let's move ahead. So here the witness looks bit. I mean, it's hard. It's a bit of a mouthful. So I'm just don't have to read this. I'll just tell you what it actually means. What we are doing is we delete all the subtrees in that complete binary tree that don't contain any of the endpoints of those parameter vertices. The parameters represent some sort of vertices. Let's say we delete all those trees that do not contain that. So what we have is a subset. You have like a forest sort of thing. And we have labelings on the leaf nodes of these trees. These trees contain these vertices which represent the parameter. And these are the ones we will basically propagate upwards. And that's the succinct sort of representation. And all the other missing pieces that are there, that are missing right now, we will somehow do some local, we'll do an ILP feasibility test to find the right number of nodes to sort of vertices to put in. Okay, so we generate those pink, orange color path, green path, blue path, red path, and so on, and all those sort of blank dots, dotted lines, they are all sort of missing from this template. And now the next thing would be the step 2, which is to generate this blueprint in FPT time. Okay, so I will not read this; it's a bit. Again, there's too many conditions to state, but it turns out that we can actually enumerate this in this FPT time, f of k time. Okay, so now that finishes pretty much. Now using the blueprint, we have an ILP formulation. Now all we are looking for is tree. These vertices, the thing to note here, the ones that are in the box, okay, there are no upsets among them. They are like behaving like bags. These are small tournament digraphs where there are no upsets. So all you're looking for is this many number of vertices who form a directed acyclic subgraph among them, and they can be attached to this red vertex here. Like this guy loses to this guy, and there are enough of these vertices who lose to this guy, under whom this tree can be attached. Similarly for this, and this. Okay, so if you can find a feasible ILP solution, you have actually created a solution, and otherwise you don't. And I'm done. Okay, so that sort of gives a very brief, but I hope you get this point, that there's a bit of graph exploration. The like, so there are among the steps, there are some things that are really wide open. You can let your creativity fly wide. You can define your own questions. There are so many different variants. I just gave a very brief landscape of what has been studied. Obviously, we would like to keep on exploring the probabilistic setting, right? And a lot of those questions that have only been studied in deterministic setting can actually be appropriately asked in the probabilistic setting. And so that's sort of just this type of work that's starting to happen. This topic is, it has obviously some sort of realistic applications, if you like, that sort of thing. But there's a lot of graph algorithm, graph structure, sort of, theoretical work, and people who are interested in pure graph algorithm, they can also have a look at it. They just reduces to a simple graph question. And of course, from the perspective of parameterized complexity and so on, the point is, even if the graph is on n vertices, has n square edges, and all this probabilistic information, blah, 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 but there are a lot of other information that might be small and can be therefore parameterized, or you can add relevant sort of reasonable restrictions, and that might open up more tractable cases that are otherwise would not exist. So with that, I think I'm going to end. So I thank you.
We have time for maybe one or two quick questions, and then longer questions we can take later. So the domain fixing for it is just a decision problem, right? Can you fix it or can you not fix it? And many of the tools allow you to introduce some optimization. For example, if I wanted to fix it without using any of the upset arcs, let's say, would the techniques allow me to do this? Because I mean, there's an ILP, so can I put an objective in the ILP of this sort or something, like,
That's actually a really nice question. So objective variants have been studied, especially that school-based. This thing that Juhi, Merav, Henry, they have studied. We have looked at demand fixing. The objective variant would be, well, okay, you can't schedule all the demand matches. Can you maximize, like try to schedule as many as possible, and so on and so forth. That's proven to be fairly early. I have not thought about the way you are phrasing the question, that is minimize the number of upset arcs.
Yeah, it's more a question about the technique. Like, do the techniques kind of allow for optimization objectives to be?
Yes. If you use the number of feedback arc set as part of the parameter, then that SBA based template topology, that succinct template, that actually will be able to answer that question. I mean, I think so, yeah.
Maybe we can take the rest of the questions
Yes.
during the break time. Let's thank Sushmita again for a very interesting talk.
Thank you. Should we remove this? Something can show.
Click on this. Yeah. Okay, so just check the pointer and maybe the person might. Oh. Okay.
Management.
This one. Oh. Yeah. So
thanks a lot for the invitation. Yeah, without further ado, I'll get started on the problem. So we'll be looking at a school assignment problem. So if we have students that we want to assign to schools, and schools have limited seats. So the first restriction that we'll have in our model is that we want to assign all these students to the schools. And we'll assume that the instance is feasible, that this is possible in some way. And so in in an actual like school assignment setting, you have students have different valuations over the schools. So what we are interested in looking at is some kind of fairness based on the demographics that the students belong to. So students can belong to various attributes. They can have various attributes like race, income, or gender, and we want to be fair to each of these demographic groups. And so there's a lot of work on these kind of problems. So in the fair division literature, there's a lot of work that tries to guarantee various approximations of various objective functions and so on. So our approach will be to try to guarantee whatever objective function we care about by adding a small number of extra seats to the schools. So let's first start by defining fairness in this setting. So let's say you have two demographic groups of students, a blue group and a red group. And let's say you have two schools, one that everyone agrees is obviously good and one that everyone agrees is obviously bad. So assuming that both students can be assigned to both schools, then if we preferentially assign the blue students to the good school, or most of the blue students to the good school and most of the red students to the bad school, that's unfair. So we want to avoid something like this. But what if there was something preventing us from having a fair assignment? What if there was a river between the two schools and these students, so that the blue students can only be assigned to the good school, or most of them at least can only be assigned to the good school, and most of the red students have to be assigned to the good school, to the bad school. In this case, we won't think of this as unfairness because we're sort of hindered by the problem space itself. So the first thing that we want to guarantee is that all students need to be assigned. So we won't think of this as unfairness. Now, what if some of the red students had a boat that could cross the river, but the blue students still can't cross the river? Well, we would like to assign the red students to the good school again, but if the good school had limited capacity, we're in the same situation as the last time, where the blue students can't really be matched to the bad school. So again, we won't think of this as unfairness because we're restricted by the problem instance. So, but yeah, in this case, if we could add some capacity at the good school, we could at least assign some more of the red students, and that sort of prevents that demographic group from being left out. So let's start by formally defining the problem. So we have a bipartite graph between schools and students, and edges represent acceptable pairings. Schools have capacities, and each edge has some utility, which is the utility that the student gets from being assigned to that school. And you have some demographic groups that are possibly overlapping subsets of the students. So we will be looking at additive utilities of the students from each demographic group. And what we will be looking at, what we'll define as fairness is we will be maximizing some objective function, and this objective function can represent any non-decreasing concave function. So this kind of objective function can capture a lot of fairness measures in fair division. For example, proportionality, or it can capture the maximum. You can try to maximize the minimum utility obtained by a group, and so on. So we will be looking at proportionality. I had one more slide, but that doesn't seem to be here. But so I'll be looking at proportionality for most of this talk. I'll quickly try to define it orally. So proportionality, what we mean is if there are, say, two groups, we want each group to get at least half of the share of the utility that it could have gotten if that was the only thing that we cared about. So let's go back to the previous slide. So if, for example, the good school had unlimited capacity, the red group and the blue group can both get the highest possible utility in some assignment. But because we are limited in capacity, the only possible assignment is this one that gives the red group some bad utility. So we won't think of this as unfairness, and this is also a proportional assignment because, again, we're restricted by the problem space. So yeah, that's proportional. So, okay, so when you have some objective like this, the natural approach is to write a convex program, and you can write it and you can solve it for non-decreasing concave functions. So what we want to do is convert this fractional solution that the convex program gives us to an integral solution. So I'll quickly state our results and then I'll discuss our techniques. So what we can show is that there's a very simple algorithm that for G groups, you can get, for whatever arbitrary concave functions you have, you can get this exact fractional utility that the convex program guarantees you. And you can get that by violating the capacities of each school by 1 and some small additional overhead, but the overhead sums up to 2G, where G is the number of groups. And you have a different algorithm where, again, you have the same utility guarantee, but the total capacity violation is bounded now. So in the first one, the capacity violation can be as large as the number of schools in total. So the second one avoids that, but at the cost of a higher runtime. So we were motivated by this recent work in SODA that obtained almost proportional solutions in raised to order of G time with G log G violation capacity. So we do slightly worse in the total violation of capacities in our second algorithm, but we do it in a more robust setting. So we can, our algorithm works even when the utility functions of the students are different, when the groups can overlap and so on. And we also get exactly proportional solutions. And our algorithm also works for arbitrary concave functions. Okay, so I talked about capacity violations, but is capacity violation even necessary? So here's a simple example that shows that capacity violation is necessary to achieve proportionality. So if you have a cycle of good and bad schools alternating and red and blue students alternating, and each school has capacity 1, you only have 2 integral assignments here. One that assigns all the red students to the good schools, and one that assigns all the blue students to the good schools. So that means that the proportional share that each student, both groups should get has to be non-zero, if you want to satisfy proportionality. So that means that if you want to satisfy proportionality, you have to violate the capacities by at least 1. And you can repeat this the cycle structure G times to show that if you have G groups, you need at least G over 2 capacity violation. And you can also separately show that even deciding whether there's an assignment that achieves proportionality with 0 capacity violation is NP hard. So yeah, if there aren't any questions, I can start discussing our algorithms. Okay. So here's our first, sorry.
Right. So the constraint the first constraint is the proportionality constraint?
Yeah, the first constraint, if you maximize, so yeah, I had a slide for that, but that's missing. So if you set f to be the logarithmic function and you maximize that, you can show that the resulting fractional solution is proportional.
So what is the first constraint? I don't understand.
That's the objective. Right?
Yeah. So
okay.
If you maximize the utility, then you can show that the fractional solution you get will be proportional.
Okay.
Okay, so let's assume that we solve the convex program, it has a feasible solution and so on. And so now we have some fractional solution that satisfies these constraints. So we can look at a vertex solution of this LP and keep fixing integral edges to 0 and 1. And we get, let's suppose we do that. So the observation that we can make is that this LP has very few constraints apart from the capacity constraints and the variable bounds. So we only have G constraints for the utilities. So what we can show is that these fractional edges form an almost maximum degree 2 graph. So except for some 2G edges, you have almost a graph with maximum degree 2. And the proof of this is pretty simple. Like I said, it's just the fact that the LP has very few constraints. And we know that now the variable upper and lower bounds are because we assume that we already fixed all the integral variables. And so we can just remove these fractional edges from the graph by by adding some extra capacities. And the way we can do that is, so if a student has a fractional edge adjacent to it, you add one capacity to that student's favorite school, and that student can be assigned to that favorite school, and this satisfies all the capacities, all the utility constraints. And so after doing this, we have a graph with just cycles and paths because it has maximum degree 2. And this is very similar to what was done in gap rounding by Lenstra, Moyes, and Tardish. Okay, so yeah, we already said that we can do this, but what do you do now? If you have a graph with maximum degree 2, that means that each school is adjacent to only 2 students. And we know that since the solution, the LP solution was feasible, it had capacity at least 1. So if you just let the remaining students pick their favorite school, you will only violate the capacities by 1 more. And then there's also the 2G factor that we already have. So that's very straightforward. And for practical applications, I think this is still very acceptable. In school assignments or like course allocation problems, adding a capacity of 1 at each school is not that difficult to argue for. Okay, but in a theoretical sense, if we still want to decrease the total violation, what can we do? So the first step that we did is still okay because we only violated the capacities by 2G. So the second part is what we want to focus on. Let's look at a simple case where after we do that, we have just 1 cycle. And let's also assume that every school in the cycle has only 1 seat left. So what do we know from the structure of the LP? We know that every student in the cycle must be fully assigned from the LP constraint. We know that because every school has capacity only 1, it must have exhausted its capacity. So that means that the LP will put some alpha weight on the odd edges of the cycle and some 1 minus alpha weight on the even edges of the cycle. So we can reformulate it in a more appropriate way. So this is what it looks like. We have alternating students and schools and alternating weights of alpha and 1 minus alpha on the edges. Let's look at the students as being as lying between the intervals 0 and 1. So if there are 3 students, let's give the first student the interval 0 to 1/3, the second one 1/3 to 2/3, and so on. So we can think of our solution, our LP solution, as fractionally coloring this interval. So let's say that, say for the first student, we gave it alpha to the odd school and 1 minus alpha to the even school. By that I mean alpha to the school on the odd matching of the cycle and 1 minus alpha to the school on the even matching of the cycle adjacent to the student. So we have a fractional coloring of this interval. So we can think of coloring the interval red if we assign some weight to the odd matching edge, and blue if we assign some weight to the even matching edge. And we know that this fractional coloring achieves a fair utility for all the groups. So what we want is to translate this fractional coloring to an integer color. So what does, and note that from what I assume that the schools have capacity 1 and so on, the integral colorings that don't violate capacities, there's only 2 of them. One that assigns every student, that colors everything red and colors everything blue, or assigns every student to its odd school and every student to its even school. So other integral colorings would look something like this. Let's say that we assign the first student the blue edge, the second student the red edge, and so on. So note that the school between students A and B, that school had capacity 1, but now it's assigned 2 students. So there's a violation of 1 there. So what this means is that the number of color switches is sort of approximately up to a factor of 2, it's the number of capacity violations. If you're switching from red to blue, in this case, it doesn't give you a capacity violation, but if you switch from blue to red, you do get a capacity violation. So again, reformulating this, what we want is an integral coloring of the interval such that we have the utility constraint satisfied and we have a small number of color switches. And what you can show is that because you only have G constraints, you can convert this to an integral coloring with small number of color changes. And this follows from this well-known theorem in the K-cutting literature, which basically says that if you have G probability measures over the interval 0, 1, then there's some subset of the interval such that all these measures get alpha fraction of their whole value over the 0, 1 interval. And this X set is a union of at most G minus 1 subintervals. So the idea I want you to take from this is that we can sort of apply this by looking at the utility of each group as a measure across 0, 1. And then what we'll do is we'll apply this theorem, get this set X alpha. And once we get that, we can think of X alpha as the region where we color the interval red, and the complement of this as the region where we color the interval blue. So that means that there exists a coloring with order of G cuts. So that means that exists a coloring where we have order of G color switches. But that still doesn't say anything about how we can find it. Unfortunately, the only way that we know how to do this is through brute force. Okay, that's one part of the problem. The other part is I assume that there was only one fractional cycle. So each cycle can be dealt with by adding order of G extra capacity. But if we have many cycles, that really ruins us. But what we can show is that you can reduce the number of cycles to at most G. And that's, again, it follows from the fact that you can write this as a linear program, and each cycle sort of gives some utility to each group. And since you only have G utility constraints, you can argue that you can only have G fractional cycles. So that gives us our final theorem statement, which is that we have G fractional schools and G fractional cycles, and in each of them you can deal with them by adding order of G extra capacity, and that gives us the order of G squared bound that we need. If there aren't any questions, I can just conclude with some open questions from our book. Okay. So the first one is, so the theorem that we applied to argue that there was some coloring with or only a few number of color switches, that was basically an application of the ham sandwich theorem. And there's not much hope to solve the ham sandwich theorem in general. By that I mean finding the hyperplane that cuts these measures in half. There's not much hope to solve that in general, but the instances that we create are much more structured. So it's possible that you can solve this in better than n raised to order of G time. But as far as I know, there hasn't been any applications of this where they do get better than this, but I would love to know if any of you have experience with that. And the other thing is, which I also haven't seen any examples of, is so the ham sandwich theorem or the application of it gives us a coloring with order of G times or order of G color switches, and that's sort of the best possible that you can do. But we don't need to necessarily do the best possible. If we can get a better runtime by doing some constant times the number of optimal cuts, then that would still be acceptable. And finally, we don't think that order of G squared is the answer. We feel that order of G should be possible. So that would require a slightly different application of the ham sandwich theorem, which we think we can do, but we're not quite sure yet. But we feel that order of G should be the right answer. And finally, as with most works on group fairness, the treatment of an individual within a group might be very unfair. And it's not entirely clear how we can apply standard techniques to make them be treated fairly within one group. That's all I wanted to say. I'll just leave with a small note saying that we can extend what we talked about to arbitrary coloring constraints, not just the ones that I talked about, with some additive loss in the constraints. Thank you. Questions?
Something I'm confused about. So bounds are not school, like the bounds are the total violation over all schools, right?
Yeah. So the first one, for example, the first statement that we have would be a violation of 1 per school,
Right.
and then 2G overall on top of that. The second one is the total violation.
And do you have any lower bounds for how much violation you need?
Yeah. So the example I talked about initially with the cycle, that shows that order of G, you need at least omega of G. So for G groups, you need at least G over 2.
I see.
So, which is why I sort of think that order of G squared isn't the right answer and order of G should be the right answer.
And you have this additive objective function. I mean, it could just be an arbitrary concave function over the UKs, right? Nothing
Yes.
would change.
Yeah.
The sandwich, you don't have exact equal to alpha. If instead of exact equality for all the measures, if you have approximate, would that help? Would that imply something?
So, it might, so I was a bit loose in the technical details. We don't apply the we don't think of the measures as the utility of the groups exactly. We think of it as the differential utility it gets from us being assigned to the odd matching versus the even matching. So it might not help exactly, but is that possible?
Not for the ham sandwich, but there are approximation results for cake division, which are
I see. Okay.
which to like which, for example, are polytime and not. So you do gain.
Okay.
So there are approximation results known for
Yeah.
cake
Okay.
division. Yeah.
Yeah, I'll talk to you afterwards. I think that might help you. Thanks.
So in this setting, it seems that we're allocating students, constraints on which student to allocate to which city other than, let's say, performance constraints, but like at least for instance, there seems to be like a common this the students have a university and the universities themselves also have a very over the students and so this kind of those scores or something. So like how much of like the concept of this so to say has been studied and how exactly that is incorporated.
So I guess a couple of things. So we do have one more constraint, which is that we have a bipartite graph. So for example, we can completely eliminate the possibility of some students being assigned to some schools. But the second part that you said, viewing this as a two-sided, so we're basically only looking at this as matching with preferences on one side, and that preference is captured with the utilities. So I'm not clear. There is some work. Meghna has some work on this where you look at two-sided settings, and there you have different objectives like stability and popularity and so on. But I'm not sure exactly how these results would translate there.
Okay.
Yeah.
Thank you.
Would not have this, like, you please push the hospital assignment.
Right.
So they use iterative rounding.
Yeah, I mean, move and over might be a reference of use.
Yeah. Thanks.
One final question. Other than most follow.
All right. If you don't want to choose the best things, just follow the crowd. Okay.
Same place.
It's a simple, okay.